And here we have, that is a handout give to you today. And there's a no sections in our textbook talk about this one. So here there's a handout I copied from other reference book and provided on Blackboard. And that is the content of the reading there. So if you wouldn't be able to catch up the details, go to download from the Blackboard for kind of about 10 pages of the written statement about this. Okay. A signal flow graph is another graphical representation of the block diagrams. And sometimes this will be a little bit convenient than by simply looking at the block diagrams in terms of the finding the simplified transfer functions. But sometimes this method will be a little bit more tedious. So it really depends on which way you like. And my suggestion is, as long as you know how to do the block diagram, that should be sufficient. And learning this tool will be additional, will give you additional benefit. Okay. So here the signal flow graph, basically they have a few basic components. And before we go into the further the calculations, let me introduce you the certain components and by defining certain terms. Okay. So compared to the block diagrams, and this one showing is the corresponding signal flow graph. And before we go into the detail, if you look at this kind of the graph, the configuration, that pretty much have the same configurations. For example, this loop is provided by this, okay, this loop provided by this, and then the input represented by this node, output represented by this node, and the lower branches basically is kind of the represented by this. So kind of graphically they are pretty much identical, but just kind of converting into the different format. And what kind of format? And here we're using the node. So here I put the dot here, and then that representing is a node. And this another node we can put here, okay? And between the node and that is the, for example, from here to here is feed forward loop, sorry, feed forward path. So from here to here we call the path, okay? Along the path, and this is the multiplication of G1 here, so that is a G1. And G1 here is called gain in the signal flow graph, okay? And then from here, from this node, we have the feedback loop. So from this node, and we'll put this node corresponding to is here. So between the two nodes, there's a feedback loop. So from here, we have a feedback loop. So the arrow here indicate is the flow of the signal. And so from here, this is the feedback. So you have to going back by placing an appropriate arrow to indicate the signal flow. Okay. So again, from this node to here, forward path, and that's a G2. So G2 is on the forward path, and on the feedback path, and that is H2. So that is the feedback path here. Okay, so right now I have talking about is nodes gain and feed forward path and feedback path. Okay, so basically there's a node gain and path here, and so those are the corresponding the terms in this one. Okay, that shouldn't be hard. So graphically, I believe everyone should be able to convert the block diagrams into the signal flow graph pretty easily. That pretty much is the kind of configuration-wise is one-to-one mapping of the information. Okay, and now with those kind of fundamental introductions, then we can begin to introduce a little more algebra. Here is the terminologies here, and again, this is the node. Each circle is called a node. Then here is the input node. This is the output node. And basically, this is the input node, and from here, the gain, if that is equal to 1, basically this node equal to that node, okay? And this is called the path, and this is called the, from here, this is called the path, okay? This is called the loop gain, or sorry, this is called the path gain, okay? And So this is the output node in this example here. This output node has only one incoming branch or incoming path. So that means it's I indicated here only one. But for maybe let me maybe compared to this node, for this node you can see it has two incoming paths. Okay, so that's one example here. So this is the one loop, and this is a one loop. Basically, the one loop you can artificially out branch. For example, this node will be equal to this node as long as this gain equal to 1. Similarly, this node will be equal to this node in magnitude as long as the gain equal to 1. So you can freely to outreach of any node as long as you put a gain equal to 1 there. This is a special case, and this is the information going here. So basically, this is called the loop gain, and that is the this is some kind of special kind of situation. It kind of give you this do exist, and so for this case, we can see this is another loop. Okay, configurationally, and that is a loop. And the loop is starting from from YQ and will be ending up to YQ again. So this is the complete loop, and we can look at the loop gain. The loop gain is here. This is we follow the arrow. So this is A24 and multiply with A3 or A43 and multiply with A3 to come back to here. So here the loop gain is multiplication of the three numbers. Compared to the loop gain for this case is only A44. Okay, and for here another important thing is we define as non-touching loops. Non-touching loops, that means any two loops they do not share any common nodes. For example, for this case, this loop and this loop they are not touching because they don't share anything. However, these I think this only one, the only loop, the loops are the two here. Okay. Keep those things in mind, then we'll begin to work on the algebra. So, for example, here for Y1, for these configurations, we can say in terms of the Y1 here, for Y1, basically Y1 has taken up how many incoming nodes. For Y1, it has the 1, 2, 3, 4, and so we'll look at here. So let me get this one. Okay, we'll simply look at the Y1, this node here. Okay, and that one, we see this is a 1, 2, 3, 4, 4 incoming. So this one is this branch. Okay, that path, and that path is this one, and then A31. So that is this one. So that's accounting for this one. A41. So that's accounting for this one, and then A51. That is to account for this one. So basically, this one taking is the summations of the all incoming nodes. Okay. And now for this example here, basically it's saying YQ for this case is the summation of the incoming nodes. So that has a 3 branch and the 3 passes. So basically YQ is equal to A times Y1 plus B times Y1, etc. So that equivalent is Y2 equal to A plus B plus C times Y1. Okay, and equivalently, that is this one. And for this one, Y4 equal to Y4 equal to this gain, multiply this node in turn, multiply this gain to this node in turn, multiply this game to this node. So basically y4 equal to the multiplication of the 3 games and multiply with y1. So that means y4 to y1 we can simplify to this. Okay, very easy, very easy. This kind of multiplication algebra is very the same as the block diagrams. And so now for this example here, and we can try to exercise and put into signal flow graph. So here we put a note onto and that is our dot. We working in the block diagram. So here is node here. Okay, so R we put a node here, and then here is E. So E we put a node here. So from R to E here, so that is E. So from R to E, there is no gain. So here is 1. Okay, we follow from E to Y. So from E to Y here, the gain is G. So we put the G here. Okay, and then from here we stretch out the Y to here. So basically the two are the same. If you don't want to plot it, that's okay. Okay, these are equivalent. Okay, and now we from here, from Y we have the feedback to E here. So from Y, we feedback the information to E with the gain. And here is a minus times H. So we put a minus H here. Okay. And here the follow-up is the similar example here. I simply place the certain variables on the block diagram corresponding to that is the node onto the signal flow graph. Okay, once you identify or define your the variables or define your nodes, you simply follow the configurations. Okay, so that is the one here. So here is more example for you to exercise. And now we gradually will get in ourselves ready for the how to use the signal flow graph for calculations. So the basic rule is this: the output, any output node at any node at the downstream of the signal flow graph, and that's called the output, compared to the signal, the node onto the upstream, and that's called the input. Okay. The output, as always, is the multiplication of the gain multiplied with the input. So, for example, this is at the downstream, so that is in terms of the output as a signal flow, and that is equal to, for this case, is a gain multiplied with corresponding node at the upstream. So for this case, Y2 equal to the summation of the information coming in, and from here is 2 paths, and on each path is A12 times Y. This is minus B12 times Y, so we come to here, okay? And that one, we using the algebra, Y2 equal to equivalently this gain multiplied with Y1. So this one can be simplified to this. Okay? And now for this one, again, the Y3 equal to A2 times Y2 in terms of A1 plus Y1 times Y1. So we have this equivalent. And the same thing here, the Y3 equal to A times this node. Y3 equal to A times this node, and this node in turn is the summations of the two past informations. So that equivalently we can simplify is A times A and A times alpha, go to that way. Okay. And for the last case, a little bit here it is here. So for this case, how can we show that equivalent is to this one? Again, we simply work on the algebra. X3 equal to X2. Okay, and X2 will be equal to, again, X2 have the two in common. One is here, one is from his own. So X2 equal to X1 from here and plus L times X2. See? for this information is simply to take this information flow from here and from here. Okay? So now with this one, then we simply focus on this. So here we have x2 on the both sides. We simplify. So that means from here, x2 will be equal to this information. And since x2 equal to x3, so we put this one here. So therefore, we have x3 to x1, we have this gain through here. Okay, that is very similar to the block diagram simplifications. So here we can exercise how to relate the x out to x in. So for this example here, we can see the x out will be equal to c times this node that we call the y2. Okay, and again from here the y2 will be equal to how many branches? And one branch and one branch here. So that means the first branch is d times y out and plus the b times y1. Okay, and again we can keep writing. So c d y out plus cb times y1. What is y1? Y1 have the coming from here and coming from there. So y1, the first one coming from here is d times y out and plus a times x in. Okay, so that means here, the x out, not y out. Okay, so from here, that one, therefore x out, x out. Okay, so from here we can simplify the things. So therefore x out, I simply, here we have an x out terms. I simply group the things together. So that will be 1 minus cd minus cbe will be equal to the x in, and that is cba x in. Good? So these are x out. Okay, so from here you should be able to find the transfer functions. So therefore x out will be equal to CBA and 1 minus CD, 1 minus CB times X in. Okay, so that means you can simplify. This is X in, and this is X out, and this is a gain. Okay, so this gain equal to this one. Okay. So from here you can see that procedure pretty much is the same as we're doing in block diagram. And we're simply taking from the output and then tier-wise going back and by trying to include all the informations. Okay. Be good? Okay. The final exam has been completed, designed, and then today I'm going to send you the from Blackboard information, certain information about the test. And so here is more example here. So I will leave those things to you because for this case here, I have the information been written here. So for example, for this case, the YQ equal to the information of the two pieces basically is equal to this one. Okay. For example, Y3 is equal to the inflow information, so that means this one, etc. Okay. So with those basic rules ready, I will introduce a very powerful formula, but in some way this formula is sometimes a little bit tedious in applications. So I'm going to talk about this carefully. Let me take the screen down. So here is the message rule. The way we've been prepare ourselves for learning the signal flow graph and for its fundamental properties and algebra, etc., is to get ourselves ready for learning this. This is the only formulas attached to the signal flow graph. And also in your homework too, I believe I designed one or two questions simply is about signal flow graph, and you might be able to apply this. And let me explain this one. Basically, the rule is this. It's saying the gain. Basically, this rule is to help us to calculate the gain between an output to input. So basically, if this is the output, this is the input, the gain simply is the transfer functions, right? Do you remember in our definition, we define this is the output in the ratio to input. This is defined as our transfer function. So basically, this one is saying we're going to find the transfer functions and we can use this rule. Okay, and how to do it? The formula is pretty easy and just like this. And how to explain this one? So n is the number of the forward pass between yn and y out. And so that is very trivial. So let me pick up one example there, and in the meantime, I can explain. So let me do this example. This example is on your handouts. Okay, we'll look at this example here. So that is the one showing on the pretty much the next two slides of your handouts. So for this case, for example here, we want to calculate y1, y5 divided by y1. So that means we define this is our output, this is our input. So simply we want to look for the transfer function between y5 and y1. Yes?
Did you intentionally leave out the A44?
The A44? 44? Oh, sorry. Yeah, good. No. My because this is 2. My mistake. Thank you. So now for this case, then we look in here. I'm using this example to explain. So here, once we define the y out, so here n is the total number of the feed forward between the y in and y out. So for this example, we see how many feed forward. And so from here for y1 to y5, we have one possible path is 1 here, 1. And then the other one is going this way, 2. The third one is going this way, 3. So here we have 3, n equals 3. Okay. And then we go to the next one. So what is delta? Delta, okay, so here is a very long writing. 1 minus sum of the gain of the all individual loops. Okay, so we need to identify the loops. So here, Okay, 1 minus the sum of the gains of the individual loops. So here we can draw the individual loops. So we can identify one by one. Let me get my colors and let me get my color here. So in addition to identify the loops on here, I'm going to draw it individually. So this is one loop here. Okay, and a different colors. All right. So this is the second loop. A loop is that you follow the flow graph and follow the arrow that will come back to itself. Okay. And the third one is this. Do we have more? I think that pretty much, right?
A34.
A34.
Back to Y2.
Back to here, right? So good. Good. We have 4 loops identified here. Okay. So the tricky part in applying the rule, the method rule, is you have to try your best to identify all the possible loops. If you miss one, then basically you're going to miss out everything in the remaining. You good? Okay. So now for this case, we have 4 loops. So that means here the statement is the summations of the gain of the individual loop. So the gain. So for this loop, the first green, that is the A23 times A32, right? So that is the gain of the green loop. Plus, for the blue one is A34 times A43, right? Then this one is A44 only. Then for the red one, so that is A34, A43, and A32. Be good? Okay, so now we continue. So now is to, the second term is the summation of products of the gain of the non-touching loop, or the combination of the 2 non-touching loops. What that means? So the second term is the summation of the multiplication of the gain. That is the coming from the two non-touching loops. Okay, I'm going to think. It's wrong saying. One-man talk show. So here for any the keywords is for any possible 2 non-touching loops. So 2 loops, they are not touching, which means 2 loops, they are not sharing the same common node. So here I identify the green one. These are the 2 are the only possible 2 non-touching loops, right? So here that is statement is the product of the gains. So here that means the multiplication of this loop, A3, A23 times A32, that is this loop, multiply the gain of this loop. So that is the statement of that saying. Okay, so that is this one. Then continue. We're going to find the third term is the multiplication of the gains from any 3 non-touching loops. So we need to identify 3 loops. They are not untouching. They are not touching. So from here we have 1, 2, 3, 4. In total we have 4 loops. Among the 4 loops, are we able to identify any 3 loops? They are not. No. So basically we stop here because this term is there. Okay. So we stop here. So once stop here, then you don't need to keep remaining checking. That's done. Okay. So now we done the delta. So now this one is the delta mi times delta I. So what is the delta 1 here? So we keep saying in the writing, delta 1 is the portions of the delta and on the signal graph that is non-touching with the feed-forward path. What that means? So right now we already identified 3 forward paths. So the first path is this one. Okay, let me highlight. This is the first path. So this path, along this path, do we find any non-touching loops? No, right? So you can see, and this basically is a portion of that one that is contributed from non-touching with the path. So basically for this path, everything is touching. So basically this is equal to 1. Got it? Okay, and what is M1? M1 is the gain of this forward path, so corresponding is the gain of this path, that is A12 times A23 times A34 times A45. Okay, and now we continue delta 2. Delta 2 is how about this? We taken this path here, so let me using this one. So here, this is our second pass here. So this is our second pass. So again, we identify our second pass. First of all, any loop that is not touching with the second pass, no. Right? All the loops being touched. So that means here, all the loops being touched, then here the remaining equal to 1. Okay, and then the M2 will be equal to A12 times A34 times A45. You good? And here I'm counting the weak one, the zigzag, that is our second loop. You good? Okay, now we try the last one. The last one is this path, and again, let me using the blue dot here. So that is our last path, and along this one. Okay. So for this path, let me write it up. The M3 will be equal to A12 times A25. Okay, and then we can determine what is delta 3. Delta 3, right now for this third pass, how many loops they not touching? This one. Then this one and this one. A34 and A43 and also A44. These are the only 2 loops not in touch with the third pass. Yes.
For M2, is that middle A34? Is that supposed to be a 2-4 instead?
A12, A34. Yeah, so that one, this is the game following this one.
How come there are 2 A4s?
A2, A4.
2 A34s.
Where?
No, on the graph.
On the graph, it should be 2.
Come over here.
This should be 2.
Oh, excellent. Thank you. Sorry, my mistake.
And then I think right here, that should be 2.
Thank you. Thanks a lot. Good. So now we're back to here. So this is the portions. I mean, taking the same template of this one for this. Okay, and right now we have only 2 loops, right? So we back to the template again. Right now, for attaching to the third pass, we only have 2 loops not touching. So using the 2 loops as the foundation for applying to the template here. So again, we can read again. That one basically is equal to 1 minus the summations of the, we're saying that summations of the gain of the individual loops and from the eligible loop here. So that is A34, A43 plus A44, right? Be good? Okay, now continue. Plus the second one is the product of the gains from two non-touching loops. So of the eligible loops here, unfortunately they are touching. So basically this is 0 stop here. You good? Okay, so right now for this case, we simply plug in everything to here, then that is our answers. And that is the transfer functions. Okay, and the Mason's rule can be so helpful if the system is a bit more complicated. And for this case, I think if you like, if you wish to avoid any mistake like I did here, you might be able to just using the primitive fundamental definition. You just work from here and here wise back to there step by step. That is okay as well. Okay, but again, the Mason's rule simply provide us is a very effective, but be careful. Even for my demonstration, I made some little mistake, right? So be careful about this one. If you miss one, you can screw up many of things. Okay, and for your homework, I believe the homework will be similar to this one. You can give it a try. And due is Monday, so the homework solution should be posted before the homework. Okay. And one similar question on this one will be on the exam. Okay, so you should know how to apply the either Mason rules or do it by hand correctly. Okay, so that is the things I provide to you. I think that should be good enough for you to complete homework 2. Good. Okay, give it a try. And the test should be open to the cheat sheet, and I will provide you more information. And I right now inclined to have you to prepare for your cheat sheet. So I will define how many pages will be available for you to write down something. Okay. So, okay, good.
And we can write anything on the cheat